Hello, my name is Elad Salomons and I'm from the Technion in Israel. The Technion is one of the partners in the EU Stop It project. Today I'm going to talk about the water quality sensor placement tool, and I'll start with a short introduction. The objective of this tool is to help water utilities in placing water quality sensors to establish a warning system against possible contamination. The workflow of this tool is first to design the threats and then select how they impact the network. And finally, and this is the main objective, is to identify the sensor's location to mitigate against these impacts. The research efforts for water quality sensor placement started a long time ago, almost 30 years ago. But one of the main advances was in 1998 by Kessler et al., where Avi Ostfeld was a co-author, and I've done some of the programming, was to introduce this idea of pollution matrix that is a set of pollution events that is used to then optimize the location of the sensors. This was further presented in 2004, and then in 2008 we had the Battle of the Water Sensors Network, where different optimization algorithms were introduced and compared. Several tools were formulated. Among them is the TIVA Spot, which is maintained by the US EPA. The water quality sensor placement tool is based on a model of the water network. This model is an EPNet INP file. EPNet is free and open source hydraulic simulator software. Once you have this model of the network, you define the scenarios of the contamination events, and the program builds the contamination matrix database, which is the pollution matrix mentioned before. Then the second stage, this pollution matrix is used alongside with some settings and objectives to perform the sensor placement and outputs the list of sensor locations. The requirements of the software are very common, just simple computer, standard computer with normal RAM and hard disk size. The software was tested on Windows 10, and that is also very common. Installation instructions are available in the deliverable 7.3, section 225. The output of the model can help and assist decision makers in locating the sensors stations, to evaluate the trade-off between the number of sensors and the different impact measures, evaluate what are the impact of already existing sensor stations in the network. Also identify upstreams and downstream nodes if you want to know which nodes are upstream of a given node or downstream of it. And also help evaluate what happens in cases of sensor failures, for example, due to a cyber attack. How will the sensor network will behave or perform if one or more of the sensors fail. And this is post evaluation of the model. This would be a good time to move on to the presentation of the software itself. For the demonstration of this tool, I will use the C-Town network, which is based on a real-world network. This is the EPNet model of C-Town. This is the main interface of TIVA Spot. The first thing I'll do is start a new project or an ensemble. I'll name it C-Town. Then I will load and select the INP file that we have seen before. And now we see that it is loaded. The first thing I will have to do is do some technicalities, which I'm not really going to go over here, just do it quite fast here, and we'll in a second move to the rest of the presentation. Just a few things that must be done quickly before we can go ahead with the more important information. Now we can do that. Now we proceed to build the pollution matrix, all the injection simulation. So we'll go to execution control, select the scenarios, click edit. First of all, we'll define the injection. We'll give it a name, injection 1, the injection rate in milligram per liter, and the time, start time and end time of the injection. So this is 1 hour injection. So this injection will be scenario will be used on a set of junctions. We'll select all junctions created, then add this injection scenario to a scenario set, and this will create 388 simulation. It seems a lot, but it's quite few for this network. So, but since it takes some time to produce these injection scenarios, I will at the moment keep this low number, click OK, then select EPNet simulation and click execute. As I said, this takes a little bit of time. Once this is done, I will offline make additional runs and additional simulations, and so we can use them in the next stage. So this is just going to end in a few seconds. So now the simulation are ended. You see the green icon here. I'll just show you that I have created a set of injections at different times. Each one of them is a different time, and the total simulation number is over 2000, which is also not very much, but enough for us. So now we move to the last stage, which is the sensor placement itself. We click edit, and here we have to set a few required parameters, which are the set here in red. First of all, the solver. We have to select the solver. It's not a real issue because there is only one option, so we'll do that. It's a heuristic solver. Then we'll have to select how many sensors we want to test, and we'll just add numbers here. So 1, 2, 3, 4, 5, 6, 7, and 8, up to 8 sensors in our network. Click OK. Now the objective. The objective is, of course, to protect the network, and not the network itself, but the people who consume the water. So the measure that we are going to use, there are a few objectives here, but the measures that we are going to use, the objective will be the volume consumed, or the average volume consumed by the people, because this is a good measure of how the contamination may affect the population. So we'll add this objective, click OK, and we are ready to perform the runs. So we click OK, here go to sensor placement and click execute. This will take, again, a little bit of time, so I'm going to wait for it to end. Now that the sensor placement run is ended, we see the green icon here. We can see also that the run is done. We can move and look at the results. We have two kinds of results, charts and tables. We look at the most important ones. In the tables, we have a table placement summary and the all sensors table. In the all sensor table, for each run, which is distinguished by the number of sensors. For example, this is number one sensor, this is two, three. We have the junctions that these sensors were placed at. You can see so that some of the junctions appear in a lot of these designs. For example, junction 352 appears here, appears here, appears here, here, and probably also in other places. Another important table is the sensor placement summary. And here we can see again the full the list of the different runs, which is each run is for a different number of sensors. This is the column that specifies the number of sensors in each run. If you remember, it was between 0 and 8 sensors. And we have the impact of each design. The impact is, if you remember, is the mean or the average consumed volume of contaminated water. If we take this table and export this to Excel, so let's do that trade off, and now open this Excel file, we will see we can easily plot the trade-off between the number of sensors and the mean impact. So let's look at this graph. So as you can see here, as the number of stations increases, the mean impact decreases. And this is, of course, expected. If we look at some map results, we can select, for example, to see how would an injection at some node would spread in the network. So just click here to play the animation, and you see that it will spread throughout the network. For each of one of the designs of number of sensors, we have some graphs, some maps we can show. For example, these are the sensor locations of three sensors. We can see, for example, other ones. Let's look at this is the design of 6 sensors. For this design of 6 sensors, we can see the detected events by each one of the sensors. For example, this blue sensor will detect injections in the blue area and the red in the red area. And by this, we come to the end of this short presentation. Thank you for your attention, and please don't hesitate to call us if you have any questions. Thank you very much.